about anything you want to talk about. So if you ask me a question on the test, I'll do a problem like it, since there's 4 different versions floating around out there. Try to be diplomatic. Yeah, that's the correct
From
word.
a problem like the limit problems of like x goes to something, like we did chapter 1, would people use L'Hopital's rule?
At the appropriate time.
Unless we're like told use the same method as we did.
You can use L'Hopital's rule whenever you're allowed to. So when are you not allowed to? When it's not indeterminate. What's indeterminate?
Infinity over infinity? 0 over 0.
Alright. Or
Infinity over infinity.
you can do that all night. Or something like infinity minus infinity. Remember that? Or 0 to the infinity. Or something like that. So, but you can always make it into, if you can make it into a ratio, you can then attack that ratio with L'Hopital's.
You got the final practice one.
Got copies somewhere. Anybody else need a copy of the practice final?
Yeah, I did.
Anybody else? Everybody going? Okay. All right. Yeah. 1E?
Yeah.
What did yours say? Was yours the natural log or was yours the...
Natural log is x plus 3 or x plus 3.
So if I had natural log of x minus 11, what's the derivative of that? 1 over x minus 11. So think about that. What's the idea with use substitution? You can use substitution when what's true, when what's inside the interval. So could I use substitution here to help me out? What would you let u equal? And what would du be?
2x.
So do you have a 2x in there? Alright, so let me ask again. Can you use substitution on this? What do you need in there in order to have you need a function whose derivative is in there also. In fact, its derivative has to be free to go with the dx. So if I put an x in there, now all of a sudden it's beautiful. I've got a function caught in here whose derivative minus a constant, who cares about constants, I can make them show up, can go with the dx, making the du that I need. That's the whole idea. So if I know this is true, and I have a function, if I have something like this, do I have a function whose derivative is in there? Yeah. Alright, that's all I'll say. This is all I should have to say. So you don't have a clue what the integral of natural log of x is. So you desperately want to stay away from having that. But thankfully this, I can recast it as not the integral of natural log, but the integral of u, because its derivative is in there. If I just had the integral of natural log, we currently couldn't do that at all. We can only do it numerically. We could plug it in the calculator, get some values, but we couldn't actually figure out what the functional form of that would be. Not yet. One of the first things you'll learn if you do take Calc 2 is a neat way to do it. It's really stupid powerful. It's called integration by parts. And part of me hates the fact that I won't be teaching it to you, but it's freaking awesome.
Sick, you can take over their class next semester?
Huh?
I said, can't somebody get sick and you take over their
No.
class next semester?
No, there's a lot of good teachers teaching Calc 2 next semester, so they'll be fine. You'll be fine. Anything else from the Tess, what about that one that's like, I don't know, a to the x?
Yeah, that was by E.
So let me ask you this. Let me see if I can come up with something. Well, screw it. Here's the example I gave somebody earlier today. What's the integral e to the 3x? Yeah, either 1/3 or e to 3x over 3. Why do you need that over 3?
Because you cancel that 3.
You know there's a 3 that would come popping out, so you need an over 3 to kill it. Now look at, if you hit an integral that there's not a lot going on in there, there's a function in there. Look at that function's derivative, just to get a feel. That's not what it's asking, but look at its derivative just to get a feel for how the function itself works. What is the derivative of a to the x? And that's why I gave that problem. This is a derivative rule you should know.
8 natural log.
Yeah, a to the x, natural log of 8. And that explains why e to the x is its own, because natural log of 8 is 1. It's the one base where the ln wouldn't even show up, because it basically cancels itself out. So what's missing here that you can take care of very easily? This can't be the answer here. The same way that can't be the answer there. You divide by the 3 because you know a 3 would come down if you took the derivative. So here you divide by a natural log of 8. Because you know a natural log of 8 would pop out or come out. It just is part of the rule. So obviously integrals and derivatives are intimately tied. This function especially is really close to e to the x, whose derivative and integral is exactly the same. So it's really going to look at its derivative to get a feel for how the function works, to see what's missing. Some of you guys had limits on this one, blah, 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 limits on that one. It depends on which version of the test you had. I can just plug them in. That was a flurry of activity. Any other questions on there? I know you guys are still looking it over.
Explain the last question.
Number 6. So, everybody got a slightly different take on a function that looks something like that. And everybody basically went from -2 to 2. So the question about why, and again, I think my grammar might not have been the best on that sentence, which explains why I teach what I do. What I don't teach would be horrible having teaching English. The question is, why do you not have to average left and right? Why don't you have to do both? Or why don't you have to do midpoints, which is sort of like averaging left and right in the problem itself? Why don't you have to do any of that? Why could you do left or right, or who cares? Because it's symmetric. Right? So there's a lot of trouble with really drawing your... If you want to do left endpoints, you just take the left side of the rectangle, you stop at the function, and you draw over. Of course, already I'm making a mistake. A few of you guys didn't realize if you start at f of 2 and you're like adding f of 1 or whatever, and you end up at f of -2, if you cover this whole thing, you actually have covered more than you're supposed to, because that's just one side of the rectangle. So a lot of you guys had sort of like this situation going on where you had one extra rectangle, or like you have 5 rectangles, but you've gone past the interval that I wanted done. So a lot of you guys figured out the width, but you didn't integrate it into the problem itself, which is a poor choice of words there. But you figured out the width, but you didn't use it to figure out what your input should be. If my width is 4/5, if I use -2 first, what should be my next input? -2 plus 4/5. Right? That's what the width is for, is to tell you how wide, where's the next rectangle start. That's what you use it for. It isn't just to plug into the summation formula. It actually helps you figure out what the next input is. So that's the connection between the width and the inputs. So a lot of guys just went straight for f of 2, f of 1, but that doesn't really match up with what I'm asking for. So that's why I asked for a picture. I was hoping that would kind of keep you contained, but a lot of the pictures are very vague. And which, when you're not sure, that's what's going to happen with your pictures. It's going to be vague, and you're going to go, just don't look at it that much, Jeff. Just give me points for the graph. I have a graph. I know that all too well because I felt the same way in some of mine. Don't look at this too closely. Come on. I've got a graph here. Just let it be. All right. Is that cool for that one? Number 6? I'll take that as a yes. Any other questions? I really like that on number 4 I say shell's not so good here, and a few of you guys just use shells. You're like, screw you, Jeff. I appreciate your suggestion, but you're crazy. And of course, it might be a question of, do you know which one is which? Which one's washers and which one's shell? Bryce?
Can we do one like...
Well, you said you're going to go over those anyways, right?
What's that? Yeah, we're going to do the last 3 together from the practice final.
Okay.
And then I see one, but I don't know if it's on the page 457 or 353, but the maximization problems. Do we ever get that on the final?
Oh, like absolute maximum? Or you mean optimization problems?
I mean, optimization.
Yeah, we could have applications of derivatives. Yeah. It's really just it's like an immediate application of derivative. It's not even its own. It's barely its own topic. It's you have a situation that leads to a function. You do calculus on the function, and you interpret what the hell it is you see. So I know how to find an absolute or even the local maximum is. Mm-hmm. So if it happens to come from a word problem and it happens to describe profit or something, then you should be able to take that extra step and say, well, that then must be the maximum profit for this interval of widgets or whatever. Does that make sense? So totally we can have optimization. I think it's at the end of chapter 4.
Isn't that kind of what the problem number 3 in the practice
Yeah, 3D.
Yeah. You want to do that one?
Might work that way, but the weird thing about 3D is you all right. So what's the first thing you want to do when you hit a problem like number 3? A position, acceleration, velocity problem. Find those 3 things. I love it. Kind of makes sense. If I'm going to ask you questions about those 3 things, you want to know what the hell those 3s are. So if I tell you the position is 9t squared minus 6t cubed, then the velocity, the first derivative will of course just be, I'm with you. Acceleration is one more derivative. Cool, right? So if you want to look specifically at part D, at least I approach part D a little differently. I don't think of it in calculus terms. I think of it in physics terms. When does the maximum velocity occur? When acceleration is 0.
When you're changing direction.
Yeah, well, not when you change direction. When you change directions, that would be what? If I'm changing direction, the velocity actually has to be 0 itself. So the maximum velocity would be when, and actually if you want to look in calculus terms, I have a velocity function. There it is. How do I maximize this function? Yeah, take its derivative, which would be acceleration. Find the critical points. Go from there.
Doesn't that give you a negative critical point?
Does it? So if I look at its derivative. It doesn't give you a negative though, right? Because it's already minus. So it's going to give you t equals half a second. And how can you argue this? I really am totally, if I don't specifically say prove it's a max or a min or whatever, you still kind of want to say something to that effect. You don't have to do any third derivative. You don't have to do any weird shit. What does this look like? What's the velocity function look like? Don't graph it. Don't get your calculator. What does it look like? Parabola. In fact, be a little more specific. Yeah, so it's going to have a maximum. Okay, end of story. So any critical numbers this damn thing has got to be the local max. Has got to be, in fact, the absolute max if you want to get technical about it. So I know I don't have to do any tests on this. I don't have to draw any number lines on this. It came from a down parabola. Just say that. If I don't say use a second derivative test or something, just say it's a down parabola. Leave me alone. It's got to be max, right? That's awesome. And then the question says, what is the maximum velocity? So what does this really mean by itself? That's the time when it occurs, so now just plug it in. Okay. That was exciting for a minute. All right.
Can you do 5?
Yeah. We'll do 5, and then we'll go ahead and do number 13. We'll do those 3. And then we'll see where else to go from there.
I guess my trouble was with the ones like from test 3, that was the 80 square foot fence with 3 sides at $10 per.
Ah, yeah, good. I love it.
One side at $21
Totally.
or whatever.
Yeah. I'll do something sort of like that. The trick with that is you have to pay attention to what I'm asking you to maximize. And then you make certain that you find that function. So a lot of you guys got really tripped up with the perimeter.
Put the function together.
Gotcha. But you just really focus on that problem. It said minimize the cost, right? So then your whole point of being, before you start doing any calculus, is what the hell is the cost function? How do I represent the cost of this thing, right? So to get there on that problem, you had the first, you always draw a picture of the situation, right? You have to label it something, and I gave you the area was whatever. One of them was 80 square feet or whatever. So then you have this little dude. So that's related to what I tell you. I always got to tell you something, because then you can use that in what I ask you. And I'm asking you about the cost, but you got to create your own cost. You've already got this shape. You knew that one side was like $10 and the other sides were like $12 or whatever the hell per foot. All right, I guess it's some standard height. Obviously, I'm not working construction. It'd be a good thing to know is how tall is this fence, right? The fence of Babel just keeps going up forever. So I've got 10x plus 12x, 22x. Anyway, I'm not going to do this whole imaginary problem here. But, so once you got your cost function set up, then you start attacking it. Right? You use this information because you have too many variables in there, and you go from there. But your whole purpose at first is to read through all my crap and say, what is he telling me? Oh, maximize the profit. Okay, I've got to get the profit function before I can do shit. So then everything I tell you, blah, 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 is working towards setting that function up. Does that make sense? I mean, that will help. There's no way I can possibly tell you how to do any situation I throw at you and get there. But if that's your goal, then you realize I don't have to worry about calculus at the moment. I just have to worry about how do I use what he told me to get this function. Does that make sense? Mm-hmm. And that's part of what people's problem was on that. They didn't know what to get.
Right. Like once I got the function, I can.
Yeah, then you can attack it. Yeah.
But I just had trouble.
So even in calculus, the hardest part is setting up the equation.
Right.
Just like it was in algebra. Yeah.
So after you find the cost function, what was the next step? I missed that.
Oh, once you get the cost function, you set it equal to 0 to get your critical points. So anytime you're trying to maximize or minimize something, it's going to occur at the critical points.
So you obviously set that entire thing equal to 0.
Yeah, well, so you got to use this to plug in from one of these, like solve for y.
Oh, okay.
Plug it in, take the derivative, set it equal to 0. Yeah. Okay, so number 5. Oh yeah, this was implicit differentiation was right before this. And implicit is normally everybody's least favorite until we hit related rates. And then that suddenly becomes everybody's least favorite. But here you got a paper cup in the shape of a cone. The total height is 10 and the radius is 3. As being filled with water at the rate of 2 cubic centimeters a second. What units would I use for this? Not units, but what symbol goes here? Do it again. dVdt, the change in volume with respect to time. I like it. Cool. I mean, the units tell you what the symbol should be, really. So they're asking me, now what do they ask me? They say, find the change, how quickly the water is rising when the water is 5 centimeters deep. So I don't know if you guys see that would be that. Here's my height. So I want to know when it's at a point when it's 5 centimeters, how quickly is that height changing? So really, with a related rates question, a lot of the beginning of the problem is use the appropriate symbols for what you're told and what you're asked, because then you can relate them to the formula that you're going to use. And this would be one where if you forgot the volume of a cone, which is not difficult to forget, you can come up and ask me, what's the volume of a cone? I love it. So this is a cylinder. Anytime you make, and here's the interesting thing, I don't know if you know this. Anytime you make what's called a pyramid, and the most simple pyramid is a cone. A pyramid is you just take all the edges and you go to a point. Well, for a circle, the edges are everywhere. So you take everything and you go to a point, that's a cone. Anytime you take a shape and you take all the corners to a single point, look at that, I draw horribly, that's not that bad. You make a pyramid. And the volume of the pyramid will be 1/3 what it was cut from. In this case, LWH. That's a cool general thing to know. Okay, good. Some of you guys are at least humoring me. So here, I got the same problem here that I had over in this imaginary problem here. I got too many unknowns. Yeah, you got to figure out, everything here is based on H. I definitely don't want to lose H. I want to replace R with H. So here at some arbitrary point, my R and my H, how are they related? Yeah, this is like similar triangles or proportionality of whatever, right? So you got 3 to 10 must equal R to H. You see this a lot in calculus problems. You see these proportionality statements you can make from the problem. You'd never want to use the specific situation too early, because then your derivatives will all be 0, of course. So you always want to draw just a general situation, label it, and then see how it relates to what else you know. So here I know R would be 3H over 10. So I can plug 3H over 10 in place of R, take the derivative, so forth. Is that cool? And once you get to this point, once you use what you're told in what I ask you, you can attack it with calculus now. So then if you get V equals 1/3 pi, or just be 9H over 100, 9H squared. Let's just make it 9H cubed. We'll have to suck that H in there. So the 3 goes in there. So I get volume is 3 pi H cubed over 100. Trust me. And then you take the dV/dt and you go from there, right? This is where the related rate stuff comes in.
Is that 9H to the third over 100?
Yeah, 3H over 10, when you plug it in for R,
Just
square it. Then I multiply by another H to make it H cubed. This is all spelled out a little better on the answer key. Remember, this is coming from the practices. dV/dt. What happens with dV/dt? Good. Not done. the part everybody hates about this. I'm taking respect to t, not respect to h, right? dh/dt. Thank God, because that's what the question is. So now when you be saved, you start to go and you say, oh, wait a minute, I can't answer the question because I don't have it showing up anywhere. So you go, oh shit, this is about chain rule, right? So now you just plug everything. At a height of 5 centimeters, you plug 5 in. That's why I had to tell you that. And then just solve for dh/dt.
By substituting dv/dt with 2.
Yeah, dv/dt is 2. Cool. Just substitute everything you know in there. Solve for the dh/dt. So let's do this. Let's do the 3 problems from page 457.
Can you, on D behind you? The last step there.
Where are we at? Is everybody cool up to here?
Yeah, real quick, so, what did you do right there?
Alright. So, if I take the derivative of this side with respect to t, I of course have to do the same thing there. And everything is a constant except for the h cubed. What's the derivative of h cubed?
3h squared.
3h squared is not dh.
Right.
So it's got to be dh dt.
dh/dt. Okay. So, and then you set that equal to what your...
So now you plug the 2 in, you plug the 5 in, and the only thing you don't know is that. So you can solve for that. Yeah.
Thank you.
Sure. So you remember that stalactite problem, I think it was? Okay, just be aware that I like that kind of problem. Because when you get the answer, you get a number, 0.2 whatever. What the hell's that mean? And there's nothing in the problem that would actually make you even want to know what the hell that means. You got the answer, just keep going. But I like a problem that really shows you, if you took that much time, that's roughly how much it would change by. That's actually what that means. Okay. But remember this, the final is cumulative. And we have less time than we normally do on a test. We have 2 hours. And we normally have, if I remember correctly, 2 hours and 20 minutes. So we have less time for this final exam, and the final is going to be cumulative. So I am not going to be able to have as long of a problem on some of these kind of problems. You with me? So I can't do a full stalactite kind of problem because there's just too many parts to it to devote to this one topic when there's so many other topics I have to hit. Graphing problem, right? Like finding the first derivative, find the critical points. I'm going to have to somehow make that a quicker process, or just throw a whole chapter out or something, you know. So it's a judgment call. I haven't made the final yet. If you can't tell, yeah.
Can you finish the maximum velocity one? I get a negative velocity. I don't think that's right.
Why not? That's fine. Well, let's see. Velocity at 1/2 is half of 18 minus a quarter of 18. All right. So 2/4 of 18 minus 1/4 of 18 is 1/4 of 18. So you should get 4.5 meters per second. I don't know if you guys have noticed this, but this kind of thing happens a lot. You get stuff like this. It's really, I don't know if you guys caught what I just did there, but it's a really cool way to look at this. This is a whole 32 minus a third of 32. So this is like 3/3 of 32 minus 1/3 of 32 is 2/3 of 32, which is just 64 thirds. I mean, you know, it's not that big of a deal, but it's just a neat way of looking at when there's a number kind of repeated there. You can kind of look at it as fractional parts of that number.
Say that again?
So if I had a whole 32 minus a third of 32, that would be 2/3 of 32, which is 64 thirds. Just a quicker way to do that. Or not. Doesn't really matter. Okay. So let's do the problems. The number 13 on the practice final. And then I'll give you the answer key. But these are the three that are not on the answer key. Just want to do these together. Now, even before we do anything, even before you start to consider what that thing looks like, before you do any algebra to figure out where they meet, all that kind of stuff. If I was going to use shells, can anyone tell me it would be integral d what? I love it. And if I was going to use washers or discs, it would be integral dy. This is the easy one. This is the guy that says, if I'm rotating about something parallel to the y-axis, or the y-axis itself, obviously, it'll be dy, and if it's x-axis, it'll be dx. Shells is just the other way around. And that makes sense, because sometimes I'll have a situation where I can't solve, so I want to have some other method to do it, where I don't need to solve. So which one do I definitely not want to use, or it would be a little more difficult than it has to be? Yeah, I don't want to do dx, because I've already got a function of y that I really don't want to solve for y. You guys kind of with me? If I'm saying dy, everything in here has to be a function of y. Well, this is a function of y. Do I want to make it a function of x? Not really. Because what will happen a lot of time is you'll have to break it up into the top half and the bottom half, because you get a plus or minus. So you'll actually have to have more integrals than you really need. You guys kind of follow? I mean, there's nothing that says you can't use this method. In fact, I might even say, use this method. Ha ha ha. I probably won't. But if I did, you could still do it. You have to break it up, though. What is this thing? Take a minute and see what this kind of looks like. Do some algebra, figure out where they meet. Those two functions, where they meet. And try to draw a real rough sketch. Sam, it's good timing. Thank you. We're doing the last problem in the practice final because it's not on the answer key.
Awesome. Thank you.
Mm-hmm. So if you do the algebra, what are you guys getting? So this should be a very familiar thing for these kind of problems. And the ones where they say find the area between these two functions, you have to see where they meet, so you know what the hell bounded, in this case, means. So if you solve that, you get a nice little factory problem here. So they meet at y equals -1 and y equals 2. So that's where they cross. And that's going to help me actually get a rough sketch, because those are some anchor points I can make sure I get. What shape is this going to have?
Parabola.
Parabola that does what?
Sideways.
Good, like that. Positive direction, right? I love it. And it's been moved over once. You with me? So I kind of know what that looks like, and of course this incredibly knows is going to be a line. So I know they're going to meet at y equal to -1 and y equal to 2. So at -1, what's the value? Since they meet, it doesn't matter which one you use. Right? So at -1, this is 2, and at -1, this is 2. It's a good check. So at y equal to -1, I get x equal to 2. And when y equals 2, I get x equal to 5. All right, so one of these things is a straight line. Since I've already got 2 points, that part's done. Yay. All right, so don't put any thought into that. The other one, just to be a little more precise, its vertex is going to be at 1. Is that cool? Because it's been moved up by 1, so it's going to look like that. So there's my region that I'm talking about. Yeah.
How did you know? Oh, how did you know to go this way rather than that way? Because it's parabola.
Because it's positive. Same way I know when it's up like that or like that. Right? So if it's x equal positive y squared, x equal negative y squared,
So if it was negative y squared, it would have made those on the other side.
it would have been over here maybe. Like if it was like 5 minus y squared, it would have maybe done like that. Yeah. You okay? You good? Yeah.
I am. Yeah.
Oh, okay, sir. Alright, so then I'm going to rotate this about the y-axis. And we've already chosen, we can't do shells, we're definitely going to do washers. We've got everything in terms of y. So what are my limits? So one of the first things we did was figure out what that's going to be. Y goes from -1 to 2. And in here I need my R inner radius, my outer radius.
So your inner is going to be 1 plus y squared.
I like it. My outer is going to be y plus 3. Inner is 1 plus y squared. Is everybody with me on this? I mean, this is... So you go through a little process about which method do I want to use. And sometimes it takes a little more thought than this. This one was semi-easy to figure out. But possibly once you start to graph, you draw the rough sketch and you start to put things in and you go, wait a minute, this is not going to be easy. Let me try the other way. That will happen. You got to let that happen and not feel bad if it happens. It's just the way it is. But you try to figure out a good way to start attacking it. You figure out the parts you need for that process. You need the 2 radii in this case, right, related to my rotation axis. And now I just plug it in there, r outer squared minus r inner squared. And like so many things, this should be the easy point, right? Just getting to that expression was the difficult part. Now, real quick, we'll finish that out. It'll be really exciting. But if I wanted to do shells, I'm going around the y-axis. Do you see how there's a couple things that are kind of evil? First, I'd have to go between the upper half and the line, and then at this point, I have to shift to between the upper half and the lower half. which again, not impossible. You can completely do it. And depending on the function, you might have to do something like that. Maybe you have a function you can't integrate it in this form, but remember the other way, the shell method has that radius, which very often is an x or a y, and that might be the chain rule piece that's missing to do that. Does that make any sense at all? Maybe. But this is the kind of thing that you really should be okay with, trying something, that ain't going to work, scrapping it and just starting over and not getting anxious about it. I mean, that's just part of the process. You don't notice until you're about here. You go, shit, that's not a good way to do it. Let me try a different way. So to finish this out, you just got to... This is the boring part. Minus y4 minus 2y squared minus 1. Right, there's some like terms, and you do the integration. This is definitely the boring part. This is almost too easy to be interesting. Am I correct in saying that? It's a polynomial, easy stuff, almost busy work. Hopefully nobody has whatever, man. Let's see, you got 8 plus 6y minus y squared minus y4. Just to go in ascending order for no reason. And then this is not too bad, right? What's the interval in this?
$8y.
8y. I like it. Good start.
3y squared.
Good. 3y squared.
Then minus 1/3 y.
Good. 1/3 y cubed.
Minus 1/5.
1/5 y fifth.
Oh.
And then I want to go from -1 to 2. And I'm not going to do any further. You guys just plug those numbers in. Blah, blah, blah. Now, I need to see the work. I need to see some of this. I don't need to see you necessarily every single step, but I need to see enough work. But you can always just go right from here, plug this into y1. Second calc, number 7, integrate from -1 to 2, right? Put your pi in there or not, I don't care. You can get the coefficient of pi or not. You guys with me? To check yourself, why not? Just don't forget, you make one little mistake in what you plug in. You don't want to think you're wrong when you're actually right, yeah.
I'm kind of missing. So from y plus 3 squared, how did you get from that to the second one?
Oh, so that's foiled out here.
Oh, you just folded it out.
That's foiled out there, yeah. For the minus
yeah,
3.
I
Yeah.
You start to do big F of 2 minus big F
Yeah, yeah.
of 1, then multiply that
By pi. Cool. And I saw, you got to be real careful, because I didn't see a ton of this, but I saw enough to make me worried, where there'd be something like somebody would do this, and then they're done. Yay. So what mistake did I make? I didn't do an integration anywhere. That's the main question I'm asking. All I did was simplify this. I didn't integrate. I can't put the plus c on there yet. Right? Why is this gone? I haven't done it yet. Right? You guys see that? So I saw enough of that. A few, more than, maybe like 5 people did this somewhere, and a few people did this everywhere. But just really pay attention. This is a definite process. All you've done is simplify. You haven't integrated yet. So your brain kind of says, we did something. Go to the next one. But you guys say, no, brain. Okay. Is that cool if I stop right there? You guys can. All right, is that right? Okay. I remember my old calc teacher. The rest is algebra. Let's go. So what about number 10? Yes.
It's about the test, and it has, it also has Washer method, and I was kind of lost with the inner radius and outer radius.
Oh, from the test?
Yeah, but just if you can draw like an like explain what the inner and what the outer. It's on the floor. So like this. So which one is inner? Which one is outer?
Oh. So let's say I had a region to do that was like this here. Nice egghead thing. Let's say I was going around x equal -3. You always draw your radii. I don't care which method you're doing. You always draw your radii coming perpendicular from the rotation axis out. So think about it when you do shell method. You have your shape, you have your little shell. Here's my rotation axis. Straight from there out, that's my radius. Same thing here. Straight from here out, the first one I hit, that's the inner radius. The second one I hit, that's the outer radius. Now this would suck for washers because, not suck a lot, but suck a little bit. I'd have a function here and another function there. Let's see, this would be okay for washers and shells. I'm thinking about for shells, it would be bad. For washers and discs, it would be fine. Because what would have to be integral d what? Since I'm rotating around here? Yeah, dy. And this would be functions of y, that would be perfect. Now if I was going to do the same shape, the same shape, let's see, wow. And I want to go around, rotate it around there. Then you could still do washers. Now this is where it would get ugly because then the inner radius would be on this side. It would go to that function, and on that side it would go to the other function. Right. So your inner radius and outer radius would be differently defined on either side of that line. Does that make sense? Because on one side, one function's in control, and the other side, the other. But if I do shells, how would I do my rectangle? Rectangles always have to be how related to the rotation axis. Parallel. So I draw something like this. So it goes from one function to the other function, all the way through. That's cool. Perfect. You guys kind of with me? And I locate my rectangle using, of course that's 5, Jeff, so that's, alright, screw it. There. I locate my, using y, so that's why this would be integral dy, right? Because washers would be integral dx, because it's parallel to the x-axis. So shells would be dy because I locate my rectangle using y-axis values. Is that cool? I mean, you've always got two ways to look at a class. You've got, let me memorize, when I see this, I do this. When I see this, I do this. Or, why the hell does all that shit make sense? And this requires a lot of memorization. This requires not that much memorization. Because this way, you just see what to do, because it makes sense. You know why this way says dy here, dx here. And so it all depends on how much you want to memorize.
In order to get the height of your rectangle, it would be the function on the right minus the function.
Yeah, so the height would be this function minus that function, right? Always the bigger one minus the smaller one. What would the radius be?
5 minus
5 minus y.
5 minus y. Exactly. So you always go front. You always start from the axis of rotation. In washers and discs, you go to the function itself. And shells, you go to the rectangle. How far away is it to that rectangle? So in this case, the r would be 5 minus y. Yes?
If you would just set up the disk for the thing on the left, could you do that? It would be
Well, you can't do it.
outer squared minus.
Oh, okay, okay.
Or would we be doing -3 minus outer squared?
For what now? Sorry?
Could you just set up the disk equation for that? So I could see
So let's see. Let's call this F, and we'll call this one G. Is that cool?
Yeah.
So then it would be pi integral A to B Oops. Let's do this. A to B. Going along the y-axis here. The inner radius would be what? G.
G minus negative 3.
Yeah, so it'd be G minus negative 3, so it'd be G plus 3. And the outer radius would be F minus negative 3, so F plus 3. And that one is exactly like just turned around. This problem is the same exact problem just turned around of number 4. Right? Number 4 is this problem just turned around so that thing's up and down. Yeah. So since some of you guys are rotating around y equal negative 2, some of you are rotating around y equal negative 10. In either case, you had to minus negative 2 or minus negative, you had to add 2 or add 10 onto your function you're plowing in here to get your whole radius. So please, dear God, don't make too much out of it. You've got your axis of rotation is at negative 3, and you're really just saying how far away is it from here to the first thing I hit? How far away is that? Well, this distance is the function itself. Since it's a function of y, it's going to be how far off the y-axis is my output. That's what the function of y is. Plus the 3 back here. So you don't even have to think of it as minus negative 3. You just say how truly far away is that? And put that value in. That's what that radius represents. Is how far away from the center to where I want to stop. Okay. So what about are you good? Yeah, number 10. So number 10 is actually exactly like number 4 on the test. So I want you guys to get as far as you can with number 10. Number 10, be careful. I'm talking about number 13 on the practice final. Number 13 on the practice final says do number 8, 10, and 16. So now we're talking about 10 on page 457. Can nothing be simple in this class, Jeff? Even just telling us which problem we're doing is a problem. So for the booklets out there, don't pay attention, your pencil's gone.
Yeah.
Oh, that is old school. It's got the where you can change the bigger pencils.
You got the big fat one.
That was funny.
Yeah. They can still make those.
That technology, well, yeah, they exist still in the poor schools. They don't have much money. So. me try to catch up to you guys a little bit. What do I want to do? What integral d what?
X.
Yeah, I'd really rather do this because my functions are already functions of x. If I have to, I can solve them for y, but then I might have to worry about top and bottom because it's going to be plus or minus. So if I want to do dx, which method do I have to use? Because I'm rotating around something parallel to the x-axis. If I want dx, that has to be Washer's discs, right? So again, which method says dx? If I'm going parallel to the x-axis rotation, it's going to be washers. Washers are like whatever you're rotating around. If it's parallel to the x-axis, dx. Parallel to the y-axis, dy. That's washers in discs. Shells, opposite. So if I want dx, because I got a function of x, and I'm going around something parallel to the x-axis, I have to use washers. Or discs. Right? Really the same method. You guys with me? Washers becomes discs when the inner radius goes to 0. That's the only difference between the two. Right? So you can treat everything like it's a washer and just go, oh, the inner radius is 0 here, and then it's a disc. You guys look so excited about all this. Desperately trying. So washers and discs are the ones that the d what is the same as what you're rotating parallel to. You're rotating parallel to y, so dy, so a way to use that is, if I want dx, I then know, compared to what I'm rotating around, what method I have to use to make that happen. And if it becomes too difficult to hold on to that, I then have to move to dy in this case, and use the other method. You kind of with me? So, you've got to let go of the idea that a problem is going to be, and I'm sure some of you guys already know this, is going to be clear-cut. There's going to be situations where you try something, it doesn't work, okay, let it go. Try the other thing. Oh, that didn't work, shit. Try some other thing. Yeah.
So when you say, like, use the other method...
That would be shells.
Okay.
Yeah, shells would let you have a dy here if you run into some trouble trying to keep it dx. Why do I want a dx? Because I really don't want to solve for x. I want to keep it functions of x. So I want dx here. So I can have functions of x inside.
But if we're going around the y,
I'm not going around the y. I'm going around y equals -1, which is parallel to the x-axis.
y to the -1 parallel?
Yeah?
Oh.
Yeah. All right. Good. If you don't cuss at least once in calculus class, you're doing something wrong. So obviously I'm doing something right a lot because I cuss. How do I find out where they meet? What bounded area am I talking about? Do what now? 7 equal to each other. Like, so x squared plus 1 equals 9 minus x squared. 2x squared equals 8. X squared equals 4. So x equals... I like it. Cool. Finding this, now I know my limits, plus it'll help me get a rough sketch, because I know what anchor points I want to do. I know these are both parabolas, one's up, one's down. It's going to make the sketch really easy to do. So at -2 and at +2, this is going to be... No, what's the value at -2 and 2? 5. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 1, 2, 3, 4, 5, they meet. So this one is x squared plus 1, so it has a vertex at 1, so it's there. And that one is 9 minus x squared, so it's 9, and it goes down from there. All right, so there's your football. Had a rough game. And I'm going around the line y equals -1. And I know I'm using washers, so then I know it's all about finding the radii. If I was using shells, it's all about finding my rectangles. Right? So here I start at the rotation. And I go out, first thing I hit, that's my R inner. Go out, second thing I hit, that's my R outer. So what's the outer going to be? Yeah, that function, that would get me to here. Yeah, plus 1. And then R inner. That's going to be the other guy. X squared plus 1 plus another 1 to get down to that axis. You guys with me? So I am really doing x squared plus 1 minus negative 1, but I mean, there's a lot of different ways to look at it. Just add this extra 1 length on top. Okay. And I don't know if you agree with me when I say this, but we get to the same boring place, right? Which is, now this is all interesting to me. I don't know if it's not all interesting or whatever or anything, but this to me is the boring part, because I know I got a polynomial going in. It's just going to be a bunch of foiling and stuff, but so I'm not going to make it crazy. We got to foil a billion things. That's totally busy work. So here it's going to be R outer squared minus R inner squared. And then you just gotta fold that out. Is that cool? Does anybody need me to finish that out? Thank you. Foil, collect like terms, integrate, don't forget to integrate. And then plug, what's my limits? Yeah, negative 2 to 2, figure that out back there. Good. Okay, cool. Alright, so number 16, we'll do that. There's 3 parts to it. We'll do it a little semi-quick. So we're between, this is number 13, number 16, 457. All right. And there's 3 parts to this, A, B, C. And part A says find the area between those. Part B says rotate about the x-axis. Part C says rotate about the y-axis. And just to warn you guys, I like this kind of problem, where you have one function and you look at it in several different ways. In fact, was it on the last, it was probably in the last practice test. I had that one problem that had like A through G and they all dealt with the same functions. Remember that? Just a little heads up. The difference between part A and B and C, of course, is B and C is related to finding the volume if you did rotate that region. Part A is just find the area of that region, but a lot of you guys, not a lot, a few of you guys are trying to throw pies into this thing, right? Pi is good in general, but in this problem you don't need it. It's not a part of the function. I'm not rotating anything. That's where pi comes in, is when you rotate, you get these circles. So to get this problem, what parts are involved? What do we have to do first? Find where they meet. And that's useful because I need that for B and C too. Set them equal to each other. One other thing it says is it's in the first quadrant. So be careful about that. Look for all of the restrictions. So they have to be between this and this in the first quadrant. So I got x cubed equals 2x minus x squared. So finish that out. Cool. So then you get x is 0, -2, 1. And which one can you pretty much rule out already? Yeah, it can't be -2. Because I'm in the first quadrant. Now they could be even more evil, but they weren't, which is nice. I'm not going to be as evil. I'll show you what evilness they could have done. With that first quadrant thing comes in some other things to take care of. But they meet at 0 and 1. And the functions themselves are a cubic and a parabola that's opening down. Cool. So they meet at 0. At 0, they're both 0. And at 1, they're both 1. So now you just got to figure out, where something is. So the cubic, of course, cubic, it's like that. It's going to be kind of like this. It's a bit of an exaggeration, but oh well. It's just a rough sketch. And then the other dude is a downward parabola. It'd be easier to sketch if I knew where its vertex was. And the vertex is -b over 2a. Does that sound familiar? Mm-hmm. -2 over twice -1 is 1. So the vertex is actually at 1. So that's cool. Now I know that you graph it like this. And then we go from there.
That really help you out. Once you figure out that the 2x minus x2 is the top one or the upper radius, does it really matter what it looks like?
Not necessarily.
Well, I'd say, does it really matter?
But it's good to get a rough sketch based on true properties of that thing so that you're not making an assumption you don't even realize. You know what I'm saying? But yeah, if you knew that was on top for part A, it doesn't even matter. But for part B and C, I'd rather have the correct shape so I can draw stuff in there. One of them's going to be shells, and I want to put my rectangle in there. Yeah. Doesn't have to be perfect, obviously, but it's better to be close. And when you have a parabola, use the vertex thing sometimes. Use the fact, up and down at least. But vertex is a good thing to find out real quick. In this case, the vertex was the point they meet at. Kick ass. Really easy to make a sketch. So I want to get the area in there. Right, now I got, looks like a pod person. Invasion of the Body Snatchers. But, watching too many horror movies. If I just want the area between, don't make anything big out of that. It's just going to be the integral of the top minus the bottom. Straight up. No squares, no pies, none of that crap. Right? So the top one is definitely going to be the parabola minus the bottom one from 0 to 1. Coolness. Alright, so again, that one's pretty simple, right? Is that cool? Let that one be easy. If I say find the area between these two functions, the most important thing, like Dan said, is figuring out what's on the top, what's on the bottom. And one way to do that real quick, if you don't even want to graph it, is if you know it's from 0 to 1, just plug a 1/2 in. That's 1/8. That's 1 minus 1/4 is 3/4. So this one is on top of that one. You guys see that? If I know they meet here and here, if I find a point in between, I see which one's bigger, that must be on the top the whole damn time, because they only meet here and here. You with me? Or not. You can always just put in the calculator. Okay. So then, when you integrate this, you get x squared minus x cubed over 3 minus, and you just plug in your 0 to 1 and blah, blah, blah. Right? That's not too bad. 1 minus a third minus a fourth, right? Which is something. So what is it? 5/12 thing. Okay. Good. If you get a negative answer there, you just flip them. Hopefully, is that all you've done? Is you flip the functions maybe? Right? So you should not get a negative answer there. I don't care where they are. I want to focus on part C for some reason. Yeah.
So I did get a negative 5/12, so what did I do wrong?
Did you put them in this order? Or did you have them the other way?
Oh, I think
Because then you did the smaller one minus the bigger one.
Oh, okay.
Yeah, yeah. In which case, you just go back and do this. And then technically you're right. I can't really say too much.
0 to 1? Why is it from 0 to 1?
Because that's where they meet. Did you have it from 1 to 0?
I did -2 to 1.
Oh.
Why did you cross out the -2?
It's in the first quadrant.
First quadrant.
Yeah,
Got it.
yeah.
Oh.
Otherwise, when you get 3 roots, 3 places where they meet, that's where it could have been evil. Because maybe there's another thing. They meet again back here, like so. Then you might have to do like this area plus that area, where now the top one would be the cubic. Do you see that's another place where they can be evil? I'm not even going to talk about how else they could be evil, because I'm not going to be evil like that anyway. Okay, all kinds of evils. Can anybody tell me, if I want to rotate it around the x-axis, what does that mean? Let me see. What do I want to say here? If I want to go around the x-axis, washers would say integral what? Careful. Yeah, integral dx. Washers and discs are the ones that just say if I'm going around something parallel to the x-axis, it's dx. So obviously x-axis parallel to itself. That would be washer. We already did a couple of washer problems. Right? So I kind of want to focus on this one. This is definitely going to be a shell problem. Why? Because shell, if I want to do washers, this would have to be integral dy, right? And looking at my functions, that one especially, it actually is not impossible. But it sure as all hell is ugly to solve this for x. This one I can completely solve for x. That one, you guys with me? Solving that for x, no. I mean, if that's not there, it's still bad. Because you're going to get a plus or minus in there. But putting that there, holy shit. Okay, so let's not do that. So if I don't want to do dy, I can't use washers on part C. I want you to start seeing the logic behind how to look at these problems. So I can't use washers, I've got to use shells, because if I use shells, I'm allowed to have integral dx still. Because I don't want to solve for it. I don't want to have a dy. I don't have things in terms of y. I want them in terms of x, because otherwise they get ugly. Okay, maybe. Yes?
Can you say all of that one more time?
I don't know. I think it was no. So I know if I want to use washers on part C, they would require me to do dy, since I'm doing it around the y-axis. And then parallel to the y-axis, I have to do dy. That would require me to solve those for x, so I have functions of y. That one, I'm not even sure if some of you guys could do it. Because it's not a problem you normally see done, but you actually can solve this for x, believe it or not. It's just nothing anywhere near pretty at all. No thank you. So I know I don't want to do dy, so therefore I cannot use washers. Shells is the one that would let me use dx in this problem. So I have to use shells.
Shells just for part
C,
Okay.
11. So B is fine with washers. C, I need to use shells. So that's why I want to focus on shell. We haven't done a shell problem yet. Okay. So let me redraw my little region here. It's just that simple. So this was okay. So if I want to use shells, that's going to be 2 pi. I need to figure out the radius. What else? Height. And this was going to let me. This is going to let me keep my dx. All right. Washers would need dy. Would I need functions of y's? No, I don't want that. So going around the y-axis. So how am I going to draw in my rectangle? Good. I've got to draw it parallel to the where I'm rotating, so it's got to be like this. It's like the Oliver Twist of everything. Okay. All right. Just little more robust. There we go. So this is why I'm allowed to keep dx, because how do I locate my rectangle? How do I get my radius? Because if I rotate this thing, the radius is going to be from the center to the edge. The radius is going to be x. That's why I'm allowed to keep dx. Okay, so that radius is just going to be x, because I'm going around the y-axis. Is that cool? If I was going around x equal to negative 1, the radius would have been x plus 1, minus negative 1, plus 1, right? Been 1 removed, so it would have been 1 bigger for the radius, but it's not, it's just x. The height is pretty simple. That's why personally I love shell method. It just actually flows a lot easier. What's the height of this rectangle? 2x minus x squared minus x cubed. Yeah, cool. And notice how, of course, that basically you found the height right here. You guys with me? The height is the same as the integral you would do for the area between in the region, right, between the functions. All right. The nice thing with shells is there's no squares. You don't have to FOIL some ugly thing out. Right? You can just distribute. What's my limits?
0 to 1.
0 to 1. Almost no matter what I do. 0 to 1 for x, 0 to 1 for y. Can't go wrong with the limits here. How do you guys feel about that? There's always the question of, do you know how to do the process for each one? Washers and shells. Do you know how the processes work? But then almost more difficult than that is, can you tell when to use which one? And I don't know if I told you, I think I told you this, that when I first learned this, I didn't. I didn't have a clue what the hell was going on. It was just so foreign to me. I had no idea. Right? So some of you guys are like, yes, Jeff, you have done the same thing to me. That's why I vowed. I said, I'm going to do the same thing to people. No. So I'm really sorry if it doesn't make a lot of sense. But I'm hoping it's not that it doesn't make any sense. I'm hoping it's just that you don't feel comfortable with it. That's a better place to be than it really makes no sense, which is where I was. I was comfortable in saying, I don't have a freaking clue what the hell. Yeah.
So to find the height, you just did the outer minus the inner.
Yeah, don't even make it, just do that top minus bottom.
It's just the distance formula.
Yeah, so if this specific rectangle was at 0.9 and 0.1, what's the height? 0.9 minus 0.1. But don't be so specific now. It's going to be that value minus that value. For any given x, that's
So the radius?
it's from the axis out to the rectangle you draw. So how far will that be? X, whatever the hell x is. So if I was rotating about the line x equal to negative 2, I would start at the rotation, go out to the rectangle, it's x plus 2. So you would put an x plus 2 there, then you'd have to FOIL this out, right?
And if this was about the x-axis, it would be, you'd be going from the x-axis for the radius, right?
Do it one more time, sorry.
Okay, so you just said the radius is the distance from the y-axis, right?
In this, well, from the rotation axis.
Okay, so since we're rotating, okay. Oh, okay.
So real quick, if I could figure out the functions, and I was going this way, then my radius, if I'm doing the x-axis, then the radius would be y, yeah.
Okay, that's right.
It's just from the rotation axis up to my rectangle.
So you just want the distance from whatever you're rotating around.
Up to the rectangle you've drawn for yourself, yep. So if I was rotating around y equals negative 5, I got to go 5 just to get there, plus y to get to my rectangle, so it'd be y plus 5 for the radius.
Oh, it's always x plus.
Okay. All right. So that's enough of that. So now I want to open it back up to whatever. Yeah.
Can you finish that through? Because I think I did it wrong.
Let's see. 2 pi, 2x squared minus x cubed minus x4. 2 pi, let's This is 2x cubed over 3 minus x4 over 4 minus x5 over 5 from 0 to 1. So it'll be 1, 0, make it all 0. So it'll be 2 pi times 2/3 minus 1/4 minus 1/5. Trying to read my writing. You know, like, yeah, I know how it feels. Whatever the hell that is.
I see what you're wrong.
Oh, cool.
Should the volumes be the same from rotating about x and rotating?
No, definitely not. Well, let's see. It looks like, the way I've drawn it, it looks like it's kind of symmetric in both directions, but no. This curvature here is different from this curvature there. But what my rough sketch makes me expect that's going to happen, but it's a very rough sketch. And we know about curvature now. We completely understand this about concavity and stuff. Totally different derivatives than this has. So this curvature is not the same, but I've drawn it so it looks like it's symmetric down the middle. Totally isn't. Right? Completely no. So they should not be equal. I would expect they'd be close. What do you get for them? So we got 5/12 there, and here we get whatever that is. 5/12. Oh, no. Oh, for part B. Sorry. So we didn't even do part B. Yeah. But I wouldn't expect them to be equal. Did you do part B?
I don't know if I did it right.
Uh-oh. All right.
I'm getting something weird.
So does anybody got this answer here? What's this here?
13
Say again?
13 pi over 30.
13 pi over 30?
Yeah.
Okay, cool. I got verification.
That's what I got for that one, but I don't know if I did B right.
All right, so I'm going to do B real quick. So if I want to rotate about the x-axis, I would use washers and discs, or just washers. This was 2x minus x squared. This was x cubed. So pi. Inner radius would just be x cubed. Outer radius would be 2x minus x squared. Cool. So then you get pi x6 minus 4x squared plus 4x cubed. Let me make sure. Minus x to the 4th. So then, does that look right? This is what you got so far. Let's see, 0 to 1, all the way down. Okay. Huh?
That's exactly what I did, and it came out negative.
Came out negative. Now that would be your problem. Let's see. Pi times 1/7 minus 4/3 plus 1 minus 1.